I use one more example regarding the orthogonal trajectory. We want to find the member of the orthogonal trajectory for this function that passes to the point 1, 1. So here we want to find first the orthogonal trajectories, and then we find the one which is passing to point 1, 1. To get this one, first we need the differential equation. We take the derivative of this one with respect to x. So we get here 2x is equal to c dy by dx. So I can write here my dy by dx is equal to 2x 1 upon c. So we find 1 upon c and then remove this one so that we get here as a function of xy. So to get the value of c, we again use this one. We're having here x squared is equal to cy and c is equal to y. Here we get x squared over y. We need 1 upon c, so 1 upon c is y over x squared. So I substitute the value of y upon c. I'll get here dy by dx is equal to 2x into 1 upon c is y over x squared. So x squared is cancelled with x, and we get here this equal to 2y upon x, and this is my fxy. So I can write here my fxy. My fxy is equal to 2y upon x. So important thing here, we can see that don't take this one as fxy, because here is function c is coming constant. So we must make it independent of the constant. So we substitute the value of c from here in this one, and then we simplify and get fxy. Now step 2 we go and we write the differential equation for the orthogonal trajectory. So please don't forget this one. This is very important. So I change the color for this reason. We write here differential equation of orthogonal trajectory, and that is dy by dx is equal to minus 1 over fxy. So now we substitute the value. We can get here this equal to dy by dx is equal to minus 1 over fxy. My fxy is 2y over x. I get here dy by dx is equal to minus x over 2y, and this is my differential equation of orthogonal trajectory that I want to solve it to get the orthogonal trajectory. To solve this one, number 3, we separate the variables, and we can see here we get here 2y dy is equal to minus x dx. So this is a variable separable. We apply that method, integrate both the sides. We get here 2y dy is equal to integral minus x dx. So we get here 2y, that's y squared by 2, 2 is considered 2, minus x squared by 2, plus constant c. We can write this one. We can write here my equation of orthogonal trajectory. Y squared minus plus x squared by 2 is equal to c1. And c1, c, the constant, I want to find. This is general. For each value of c, we get an orthogonal trajectory. But now here we said this passing through point 1, 1. So passing through point 1, 1 mean passing through point 1, 1 mean x equal to 1, y equal to 1. Substitute it here. We get here c is equal to 1 plus 1 by 2 is equal to 3 by 2. So we get here y squared plus x squared by 2 is equal to 3 by 2 is orthogonal trajectory, the curve passing through the point, trajectory passing through point 1, 1. So there were more examples in my notes. I'm going to put my notes in the description. You can get the link and you can just take it from there. There are also the exercise, you can do it. And again, as before, I said this important thing is that if you want to get the regular notification for the course, then you like it, subscribe it, and also press the bell icon so that you can get notes regularly, the information about our videos. So this was about the orthogonal trajectory. We get an example, repeating the example again. These three-step methods. Number 1 is that we find the differential equation, that's dy by dx is equal to fxy. So we just eliminate c and we can write our dy by dx. We get here dy by dx is equal to 2y upon x, and that give me fxy equal to this one. So the second step, very important, is to write the differential equation of orthogonal trajectory. That is dy by dx is equal to minus 1 over fxy. My fxy was 2y upon x. I just substitute minus 1 over 2 pi x, take the negative reciprocal, get minus upon 2y. This is my required differential equation of the orthogonal trajectory. Now I want to solve this one to get the curve. I just write it. We can separate the variables using separable variable, integrating both the sides. We get y square by 2, 2 is cancelled 2, we get here minus x square by 2 plus c. Then we take x square by 2 to the other side and find the value of c1. The curve is passing through a point 1, 1. So x equal to 1, y equal to 1 is passing the point 1, 1. So we can put the value of x and y here. We get 1 plus 1 by 2, 3 by 2, substitute the value of 3 by 2. So get here this is y square plus x square by 2 is equal to 3 by 2 is the orthogonal trajectory passing through point 1, 1. That's our solution. We are having the next application, that's a growth and decay problem. We are having different situations where we need to know how the things are increasing. In case of population also, in case of certain bacteria also, if you go to the hospital, they take your test and they say you get the result after 1 week. So they take the test and they grow the bacteria in the laboratory, and then they make the analysis and give you the report that which type of infection you have, and they control the infection with the help of that one. Also, we can see that the town planning, we want to know the population growth pattern, and to get for example, there is a per town and we want to see what will be the population after 50 years, we can do it. Or even for a country, we want to get the economical and other planning for that one, then we need what is the population after 100 years, after 50 years, after 10 years, after 30 years. And then you need some model, and that is known as growth model. So we use that one and we can predict it, that what will be the population after 50 years, or you can say there is a population about 10 millions, and we want to see the time, how much time to double, it becomes 20 millions. Or sometimes you can see, you get the news in the newspaper that the population of the earth is going to double in so many years. So that's the growth model which we are going to use. And the growth model, the important thing is, if we take here y as a quantity which is growing, y is a function of t, we see the quantity which is changing. So the rate is changing is dy by dt with respect to time. And the growth, we say that dy by dt, the rate of change of growth, is proportional to the quantity present y. So for example, it's a small town, and then the growth will be different from the big town. The big city, the growth rate will be higher, and the small city will be, they depend upon the number of population present at a certain time. So here we can change this to equation by changing the proportionality by a constant. We can write here this is dy by dt is equal to k times y, where k is constant of proportionality. Is constant of proportionality. So then we can need the information. One is the initial information, that from where we want to start. So the initial information, we say we take certain time, always we take t equal to 0. So we say t equal to, at time t equal to t0, the quantity present is equal to y equal to y0 at the time t equal to 0. Sometimes we write this equation combined and we say y at t0 is equal to y0, and this we call this initial condition. Here initial condition is on basis that this is starting value, is a cold condition where we start our solution. So we can get the initial value problem. Our initial value problem now, if you take this as initial condition, that we say here, our initial value problem we get, that is, we get here dy by dt is equal to ky. Initial condition at time t0 is equal to y0. This is our initial problem. We have the differential equation and initial condition. We are having here k as a constant of proportionality. We want to find the value of k, then we get the complete solution. To get the value of k, we need one more condition, and we say additional condition. We say we want to take one more condition in our problem, more information. we say initial condition, and this initial condition we need to find the value of k, to find the constant of proportionality k. So we say y at certain time t1 is equal to y1. So because when we find the solution of this one, one constant we get because we having the first order differential equation. One constant is due to this constant of proportionality. So we need two conditions. One is say our initial condition, what is the initial situation, what are the number of bacteria, what is the population of the town in the beginning, and then we can write. Then we can say, for example, the population, we want to calculate after 10 years. We say after 2 years, the population was this much. That we have T1. T0 will be equal to 0 and T2 will be 2 years 2. Then we get here after 10 years. So we'll get here the complete solution when we have two conditions. Number one, we're having the initial condition. Number two, we're having the boundary condition, and this is my differential equation. So this will make my complete problem for the growth and decay. I have given the in the growth that the growth in general we say, if it is not defined otherwise, but in general we say that the rate of change of growth is proportional to the growth present at any time. That's yt. That's dy by dt is proportional to y. We change differential equation multiplied by k, so that becomes the equation. This was the proportionality, this is the equation. Now we want to solve this equation. When we solve it, we need the complete solution. So we need a condition. Initially, that's my initial condition. And then to find k, we need an additional condition, that t1. So with the condition 1 and 2, we get the complete solution. Once we get the complete solution, and then we can solve it. I will give you the detail of that one. I give you the detail of the method, and then I will give you the example for solving the how we can apply that one. So our method is that we are given here the differential equation. The differential equation given to me is the rate of change of a quantity y is proportional to the k and is proportional to y, and we can write here ky, k is constant of proportionality. Initial condition we say we have cold start, that means at t equal to 0, t0 is equal to y0. So this give me the, when we have the initial differential equation, that give me the particular solution. I solve this one, I just multiply by dt, we get here y dy is equal to ky dt. We take y to the right hand side, I get here dy over y is equal to k dt. This is my variable separable. I integrate this one, I get here dy over y is equal to integral k dt. We integrate this one, we get here ln of y is equal to k t plus ln of c. K is constant we take. So now we can just change this one. Y must be bigger than 0. Y is always bigger than 0. We are taking, so we write it without absolute because we have put the condition that y is bigger than 0. So we can rewrite this one, and we can write here that ky ln of y is equal to ln of e to power kt plus ln of c, or we can write here ln of y is equal to ln of c e to power kt. I have told you before, then ln of m plus ln of n is equal to ln of m into n. So multiply them. So we take exponential of both the sides, e to power ln of y is equal to e to power ln of c e to power kt. Ln and e are cancelled, we get y is equal to c e to power kt. That's my general solution. This is my general solution. I have the initial condition, I use this one and get the value of c. I have when t equal to 0, y equal to y0. So I substitute this one, when t equal to 0, I get here e to power 0 is equal to 1 and c is equal to, we have y equal to y0 is y0. So I can get here y is equal to y0 e to power kt. This is my particular solution. So as I told you that we're having one more condition, that we say the additional condition, that is if we are given here additional condition, that y at any time t1 is equal to y1, this condition will help me to find k, and then I say this is a complete solution. I will show you with the help of example.